Hey folks, can everybody hear me? Oh wow, that's loud. Okay, hey, let's try to settle down. We waited a few extra minutes, let folks settle a little bit. Try to find our seats. Of course, as soon as I start talking, you're over there trying to grab a snack. Hey, so good morning. We're on day 2, which I think yesterday went really well. Hopefully for a lot of folks in this room. There was a lot of opportunities I saw a lot of folks having discussions. Did anybody have like an uncomfortable or like argumentative discussion? Clap if you had an uncomfortable discussion. Anybody? No? Nothing? Okay, there we go. Thank you. Thank you for the hand raise, David. Appreciate that. So hey, hopefully we are having those, right? Like we shouldn't be in a position where everyone's like, yes, yep, everything's good. We should all be challenging our views a little bit here, right? And that's okay. That's what this is kind of supposed to be for. Tough topics, right? I did want to share some feedback from yesterday. First one, we are going to make sure folks are mic'd up over here so everyone can hear the person talking. So if they're not, if you can't hear them, feel free to be interactive on the stage here, yell, say like, speak louder, that kind of thing. Totally fine, right? And I think really some of the things that we had in the breakouts. So if you didn't have breakout yesterday, I think some folks got to get in there. We're going to have a little bit different tune today for some of the breakouts based on the population that showed up and is part of this in-person event. So we'll have some more opportunities for folks that maybe don't have a breakout today. We'll work through some of that right before we go to breakouts. But when we were in the breakouts yesterday, just for Army feedback, if you're in the Army or if you're around it a lot, you definitely say things like, acronym XYZ is this and that, and you start talking in letters and people are, completely disconnected from what you're saying. So please explain your acronyms. And I'm an Army person. I do it all the time. I try not to. So try not to do that today. Try to explain yourself for sure. And then if we're in the industry side, we're gonna keep away from the pitches, right? So we definitely want to stick on to the technology and the problem sets and the use cases and all the things that we're talking about from a technology standpoint. But the facilitators are gonna watch you for any pitches. Okay, so stay off of that if you can. And then today we're talking. So yesterday, platform electrification, right? Air and ground had some great panelists up here. Today we're talking soldier and small unit power. So I think there was definitely a lot of overlap from yesterday as well in all the uses. We're gonna hear some more of that today, and we have a great first panel coming up. Just a couple quick admin notes for those that are new today. Again, we got the badges. Please wear them. Any fire or hazards, please exit the building. If you have an issue, please come find me or any of the Capital Factory staff, which are wearing those Capital Factory staff badges. And a couple of our key Army Applications Lab folks, if you have an issue or concern, okay? And then Q&A is on the back of those chairs, right? So you are welcome to start asking questions as soon as that panel starts, right? Go for it, and then that feeds the moderator here. He's got a little iPad up here, and he's kind of listening to those questions come in, and everyone can kind of have a chance to ask something. Okay, all right, so our first panel this morning, we're gonna get right into it. No other welcomes, just me today. First panel here, fresh take on personal power. We are exploring how next-gen energy technology can reduce the threat of lightweight, standardized approaches to power, when away from the grid, right? Panel moderator, Joseph Kopser, he's gonna come up here. He is the liaison for military affairs at University of Texas, Austin. He's also the executive in residence at McCombs School of Business at UT, CEO of Grayline Group, and prior to that, he's co-founder and CEO of Ride Scout. He's had 20 years in the military before that, just a lot of experience, and is really excited about innovation and keeping this group together for collaboration as we work on energy and electrification. Please welcome Joseph. Oh, we're gonna mic him up. So just give me a second. It's gonna be great. And then we're gonna mic up those folks back there as well and make sure that everyone's working right.
Put it on this side.
And then you gotta push that button. Yeah, it should be good.
How's that? that work? Can you all hear me?
Yep, we got you.
Yeah?
Christine, can you bring up folks for mics?
Yeah.
Thanks.
It'll take, yeah, we weren't quite mic'd up, but that's okay. I feel like Madonna or Beyonce because I have this cool thing here on the side. So if I start dancing in the middle of it, you'll have to excuse me. But the real reason why I'm going to be dancing in the middle of this is this idea, this conference, everything y'all are talking about. This has been my jam for so long that this is like a family reunion. I've met many of you all over the years in this space. So by way of introduction, while they're getting mic'd up, we need a minute. This will also be a good chance for me to meet the audience and make sure that I'm, meeting you all where you are. But it is a wide group, so let's kind of go there. So in terms of the Army, I got into the Army in '93 after being at West Point. Ironically, while I was at West Point, I wanted to be an astronaut. So I was an aerospace engineer, but as my eyes got worse and my love of the cavalry got more intense, I decided to abandon my aviation friends, and I went into the 3rd Armored Cavalry Regiment, going right out of the Army in '93. In '96-7, I was following a boss of mine that moved to Fort Hood, so from Bliss to Hood, and I ended up getting into Force 21, 4th Infantry Division. Anybody back there in Force 21 days, FBCB2? Got a couple of hands up. That was Blue Force Tracking. If you guys are ready, come on up and have a seat. That was Blue Force Tracking. And I got to watch in real time as soldiers rejected all of the equipment they were given to test, or unplugging it and throwing it out. And in real time, I was asking the testers that were there with us every time we jumped down off of our vehicles. I'm like, hey, I'm actually a computer coder. I'm an aerospace engineer. Like, I get where you guys are going. Can I help you with this? And the person stood there very nicely and said, no, just answer these questions I have on my clipboard. Okay, so that was the beginning of my time in Army Innovation in '99. It's had some ups and downs, which we'll get into in a minute. And I'll do the rest of my biography as we go through the conversation with our guests here, because the purpose of this conversation is less about their individual companies or their individual biographies or even their individual technology. The purpose of this next hour is to make every one of you all in your seats and in our seats squirm just a little bit, because we've all got to be asking ourselves, are we ready, whether you're Army, industry, big business, small business, governments, requirements, wherever you come from, are we ready to even imagine or think through some of these requirements before immediately saying, no, or this is why it can't happen? Nope. In fact, we'll keep it anonymous, but I was in a group yesterday in a breakout where somebody actually looked at another person in the room and said, that's the wrong question. And I said to myself, how the hell can that be the wrong question, as if to assume you hold the right answer or right question asking? And so what I would hope to do for this next hour is just get to a point where we're like, that's a good idea. Hadn't thought of it like that. Didn't know we could do it like this, or I've heard about that. But more importantly, what do I got to change in my own organization or my own frame of reference? So let's just jump right into it on personal power side. So Brian, with Big, is going to talk about battery safety. So big picture, give a quick background idea of your technology, and then we're going to be getting into the questions.
Yeah, sure. So,
oh, by the way, I apologize I didn't wear the gray jacket today. I did not get the message. That's okay. That's okay. Go ahead.
I bought this suit last century. And
Okay.
It still fits.
There you go.
That's good. My background, I'm a physicist. I'll tell it. I had a very short military career. I joined the reserves in 1985 in order to get my friend a promotion. He went in as an E2, left as a colonel. So good for him. I left as a private 4 years later. So it wasn't for me. My background is a physicist. So I'm a materials physicist, 10 years at big companies, and then a bunch of years as an entrepreneur. Soteria Battery Innovation Group. So Soteria Big. We are two things. The first is a technology that goes into the battery that makes it extremely damage tolerant. So think stab it, crush it, stick it with a needle, shoot a bullet through it, and the battery continues to function, which is different. Others may be able to not make it explode, but continuing to function is something that I think we're unique in doing. The other is we decided that battery safety was a universal problem. And so we've formed a consortium today, 115 different companies, NASA, Mercedes, Bosch, Motorola, DuPont, many others, who work together to put together many, many different solutions for battery safety. And as a consortium, we want to be the place where people talk about the equivalent of seat belts and airbags and anti-lock brakes and rear view cameras and radar for cars. We want to be the place where people talk about that for batteries.
And on the personal power side, we talked beforehand, give just one example or application on the personal power side.
Yeah, sure. So Fitbit, right? You wear them on your wrists. They just had a recall of $250 million of Fitbits because the batteries were delivering third-degree burns to people's wrists. It's the tiniest battery you ever saw. It would be really hard to ignite that thing. But if you make it with rare manufacturing defects, but the challenge with battery fires is spontaneous ignition. There's your pile of batteries. There's your pile of batteries on fire. Nothing happened except you went to bed that night with the car in the garage, right? People go to bed at night, cars in the garage, and they wake up in the middle of the night because the garage is on fire, right?
Yeah.
And that, if you guys think a lot of energy in a small package, you guys call that ammunition, right? If that starts spontaneously igniting, that's not a good thing, right?
Yeah. Okay. So we're now just thinking about the safety side of it and what it means when we try to put more and more energy in a smaller and smaller spot. But because you mentioned Fitbit, you have a nice little segue to Douglas and what you're doing with battery technology. So go ahead, batteryless technologies.
That's right. My name's Douglas Tam, and I'm CTO and co-founder at Matrix Industries. Like yourself, I'm a material scientist and chemist by training, in the materials aspect of things. What we have at Matrix is an energy harvesting technology based on thermoelectrics. And what we can do is to harvest the smallest temperature gradients to power electronics. So for example, I'm wearing a wearable that has our energy harvester embedded into it. That's one big vertical that we're really targeting to really take the latest and greatest in sensor technologies and algorithms, which are really low power, just flip the problem on its head, right? Just reduce the power consumption to the point where even small amounts of energy harvesting can sustain it. So that's an application where it's a health wearable in the commercial sector, but we're working with Navy, Marines, Army to turn it into a troop readiness type of measurement platform, right? The other big vertical that we're really involved in is to really take this energy harvesting technology and start to harness the temperature gradients in the environment. So day to night variations in temperature in the topsoil, we can actually harvest that to power unattended remote monitoring systems. So sensors that we embed in the ground, they're stealth, they're covered, camouflaged. We can use that to detect vibrations and to find out if there's a person, an animal, or a vehicle crossing the perimeter of a certain area. We're working with Homeland Security to deploy these to detect incursions into certain places.
Yeah.
Right. So that's that for me. Thank you.
Yeah. So, and we'll talk personal power more detail about the idea of what is imaginable if you don't even have to think about batteries. And again, I told you by way of biography, I'd lace in a couple of things here and there. So when I got back from Iraq the second time, I ended up joining FFID. Any FFID veterans in here? So Future Force Integration Directorate that was out at Fort Bliss, General Terry at the time. I was a special assistant for him, following through all that work, as well as in DC. And it was fascinating, speaking of batteries, and we've heard this anecdote yesterday, we saw it up on the screen, of just how much battery weight that the soldier was asked to carry during a lot of those limited user tests back in the day. And again, as we concentrate that down more, it becomes a safety issue. But then also, if you just eliminate the battery altogether, what's imagined possible? So Max, you have a whole nother take on personal power from what you all are doing. Tell us more about who you are and what your technology does.
Great, thanks. So I'm Max Menken. I'm the Chief Technology Officer and one of the co-founders of a company in the Seattle area called Modern Electron. And like you guys, I come from a chemistry, PChem, physics background. And what we effectively have two solutions in the commercial world. They're aimed at efficiency and decarbonization plays for people who use a lot of natural gas. One of the solutions is a box that basically converts natural gas to hydrogen. The second solution is a small, very compact heat to electricity converter known as a thermionic converter. And we've developed some new innovations on these devices that both lower the operating temperature and increase the power density and efficiency. And we're deploying those in a bunch of commercial scenarios now. So translating this to the idea of personal power, you could envision taking one of these heat to power devices that can accept heat from nearly any fuel as long as it's hot, and deploying it in a small box, say this big, shoebox size, and bringing that with you out in the field, using it to recharge batteries, using it to power up some remote equipment, whatever is needed.
I just have to ask you, use the analogy. So if I were laying on the back deck of an M1 Abrams tank at night, trying to stay warm in the cold, and as I lay on my back is on fire practically, but my face facing up is very cold, could you take that heat coming off and create electricity off of it?
In principle, yes. It depends a lot on how hot the heat is and what that interface looks like. But yeah, you could do something like that as well.
Fascinating. Okay, last little tidbit of this, or not last, last little point, I keep saying last. The next thing to say is, so then I end up in, after FFID, I end up in the chief's office, and this would have been circa 9 to 11, and that's when General Corelli, those of you that remember the story, came in as the vice and just said to FCS, and just cut it off right there. Luckily, we harvested a lot of those technologies that were being developed by industry and others, but it was dead and gone. And now for the last 10 years or so, many of you all been at the front lines of trying to help figure that out. So I want to remind everybody to ask questions. The stickers are on the back. Take a, scan with your QR code, submit them. And I've asked them to bring the iPad up to me sooner rather than later, because the more questions we get from you all sooner, the better. So let's just take one aspect, form factor. It's in the description of what we want to talk about. You hear it all the time in terms of the limitations it makes on what we're trying to do. As you have been here at this conference, or as you've already been talking to folks either in government, military, what are the biggest challenges you see? And I'm going to start on the end with you, Max. We'll go back this way. What are the challenges that you see that they are being told, that they're telling you? And what are some things that you want them to just think about? What's in the art of the possible?
In terms of form factor, footprint,
Yeah.
size, shape?
Yeah.
So my understanding of the DoD logistics chain, and which I admit is very limited, is that JP8 is kind of king right now if you want power out in the field. And the way we see that is that this is great. What that means is that one of the things that we've struggled with, candidly, as a small company, is being able to interface with whatever the standard fuel interface and power interface is. And so you can envision, we have a small generator solution. The challenge is, how do we get your fuel into it and our power out of it in a useful way? And so one of the big challenges that I think we've encountered is a very clear understanding of what those interfaces are, as well as some of the requirements around goals for weight and thermal signature. One of the speaking broadly more about our interactions with the DoD, it seems that there are so many different use cases, which makes a lot of sense, that it's very hard for us as a small company to tailor a solution that'll work for multiple groups. And so one of the things that we always encounter and run up against oftentimes is, how do we build a solution that's going to be compelling for one group, but also serve as a springboard for another group?
And by group, you're not limiting yourself to civilian versus military. You're just talking about any application, you as an entrepreneur trying to focus on the biggest total addressable market.
I was thinking more in terms of DoD. So if you talk to SOCOM, for instance, versus Army, they have very different logistics, very different requirements. And so as a small company, one of the things that we're always curious about is, okay, we have a commercial mandate to our investors, of course. And so how do we find the application within DoD that's going to provide the largest return on that investment to build that prototype and build that first unit?
Yeah, you brought up a great point. For those of you that aren't familiar with the Army in general, there is, in some ways, a difference between the big Army and the special operations community in terms of the rules, the regulations, and how something's done. Are there folks here from the special operations community in that acquisition world? I see one, I see two, I see three. Oh, good. Oh, see, they're hiding over here. I like that. But they're really not hiding. They're perched in a location such that they have the best overwatch of the whole group. I would expect nothing less of them. Excellent. So it's good to know that y'all are here too, because again, there are differences. All right, so Doug, form factor, especially the batteryless technology you described, what's in the art of the possible that you want people just to imagine? And again, not just limited to your company, your technology, just to push the envelope for discussions later today.
Right, right. So one of the things that I've come to realize that in Army speak, the prime mover of any campaign or whatever you're doing is really at the troop level, the human, right, the soldier. And I like to try to kind of flip it around a little bit. What recent events have taught us is that we can actually rely a little bit more on sensors with a lot of persistence and loitering capabilities, right? So imagine if you could deploy swarms of sensors that do the work for you of keeping watch at night or in the day, all day, every day. Then it frees up the soldier, the thinking human, to do other things, right? Rather than bogging them down with, guard duty. So that's one thing that we have really tried to look at. Taking like I said, the latest and greatest, taking sensor systems and putting them into really low power applications that we can either get rid of the battery entirely or shrink it to such a small extent that it's essentially just a capacitor to mitigate some of the spikes in consumption. That's what we've been able to do with our commercial type applications. Like Max here, one of the things that we struggle with is to understand the divide, I guess, between the requirements. So of course we were going for the commercial sector first, but trying to find overlaps where we can take that commercial technology and rapidly turn it into something that has applications for military and defense related stuff. That's been a little bit of a challenge, but I think that there are obvious overlaps that we found in recent years. So yeah, I think that's what I would like us to kind of step back and say, hey, let's not have a soldier who's tired, who's overburdened with stuff, do all these things that we can actually rely on new technology to do, to really outsource it, so to speak.
Doug, are you trying to imply you were there with Apache 1.6 at the National Training Center when I fell asleep against my night vision device inside the Bradley? Is that what you're trying to say?
Well, I can't speak for
Okay,
what
that may or may not have happened. Oh, good, we got questions coming in? All right, good, we'll get to these in a second. But you mentioned, for a second ago, you mentioned Army speak, and I think that's incredibly important to make sure we understand what we're talking about in terms of Army speak, civilian speak, the differences. I've now been out of the Army for almost 10 years, and so I've lost almost all my ability to communicate fluent Army, and I've only been in the private sector for about 10 years, so I can't even say I can speak fluent private speak. But the good news is I've hung in both of those communities for so long that I'm functionally literate in both. Okay, I can generally read body language. I can generally learn tone and know when I've either stepped in it or not. And so far, I don't think I've stepped in it yet, but I hope to. That was my goal. I told you I wanted to be a little bit edgy. But Brian, let's talk form factor. What's in the art of the possible that you want people to think about, or if you could just make, wave a wand for these discussions later today to really push the edge?
Yeah. So what I see a lot of, right, talking to the different consortium members, is a drive to put more and more energy and more power into a smaller and smaller box, and then put it closer to the body, right? So think headsets with a battery sitting right here, right? If that goes off, and if it goes off like the one that your wrist, that Fitbit did with the wrist, you're gonna lose your sight, right? And so the interesting thing is that while they're cramming more and more energy, so think twice or three times what the energy of an existing lithium-ion battery is, or a third of the size to get the same amount of energy. And that's what folks like Amprius is in the room that they're doing. But we have other guys who are doing liquid electrolyte lithium metal batteries that can survive that can survive damage, so survive a nail penetration test without going off. I guess the point at the end of the day is more and more energy in a smaller package is happening. It's ending up very close to the body, right? The example in the military is the conformable wearable, and we're working with both Amprius and Navitas to get our stuff into their cells. So we're kind of behind the scenes, kind of trying to let it seep in. But more and more energy in a smaller package and then close to the body. It seems dangerous, but I think of safety as a multi-level solution, and there are enough levels there to make that fail-safe, right? To make that possible and doable without issues, but it won't require, there's no magic bullet. So I'm a fan of solid state. Solid state is one of the things that is sufficient to deliver safety, as long as you package it with all the other things also, right? And so it's a multi-level solution, but when it's done right, you can put a lot of energy right next to your body or inside your body in some cases, and have it and put a lot of energy in there and have it be safe.
Yeah. On this idea of form factor or blending the two worlds, military speak, technical speak, or whatever you want to call it. I was served on a board of a company that was looking at personal power harvesting around the knee. There's folks doing it around the ankle, doing it around the knee. There's all kinds of different experiments, but I thought it was fascinating that I could see where they're going with the technology. I get it. I know it. But I also know that walking around with enough equipment around your knee can be cumbersome. And if you're not generating that much more power, a soldier's going to take it off. They're going to take it off. They're going to put it in their rucksack. And then eventually at some point, when you get back to the Rough Mother Ruba after a training event, you're going to find it in well, I won't say where you'll find it, but it'll be right next to all the spent MREs. Okay. So let us jump into a couple of these questions. Oh yeah, so let me say it again. It was interesting. So who is chairing this session? I can't see it on the schedule, and that I do apologize for. Late entry as the moderator. So again, my name is Joseph Kopser, Kopser, and that's who I am. You can find me all over LinkedIn and whatnot. Big fan of defense innovation, especially after I got out of the Army. Work with a person you may know here, Craig Cummings. He's my business partner, also Army, also West Point grad. Sold our company to Mercedes. From that, we did two things: create an endowment up at UT for student veterans that want to leave the service and create their own companies. See me about that afterwards. And the other thing that we did was turn around and pay it forward. So he is a VC investor, and I am a serial entrepreneur working with VCs. So that's who I am. I should also say a dad with 3 adult daughters. Last one's about to graduate next month, off the payroll, done. It is literally like picking up another business client, having paying no more tuition, no more anything. Okay, what is the thermal efficiency of the thermopiles? Did I pronounce that right? Thermopiles. And what is the max and minimum temperature range?
Oh, for me, right?
Well,
So
yeah.
it depends on the application. For the stuff that we focus on near room temperature, we typically run them below 250 C, right? And the efficiency obviously scales with temperature. I mean, this is thermodynamics. So at near room temperature, it's almost nothing. It's like 0.5% maybe. But if you're dealing with free energy that's already in the environment, it really doesn't matter. If you're able to crunch down consumption, it really doesn't matter. So if you're thinking of this as a primary power production play for thermopiles, I would say, yeah, we're not quite the greatest fit. There are a lot of other companies here that are involved in primary production of electricity. So, we're really in the energy harvesting space. Our focus is on low temperature gradients, and that's where we see the biggest advantage.
Okay. And for non-thermodynamic students, just give one quick use case where, bam, your technology is going to be like, whoo, so great we had it.
Right. I go back to the whole unattended remote sensing application that we're working on. We are just harvesting temperature variations in the environment. So you're talking about midday sun, the soil is heated up by about 20 degrees Celsius against the nighttime temperature. So that's how we can actually remove the need for battery replacement. So if you put the sensor out, you never have to change the batteries.
Got it. Okay, that's very helpful. All right, so let's see. There's another question for you. So let me skip that for a second. I'll come back if we run out. By the way, we doubled the number of questions, so I applaud y'all for adopting this new technology. It's pretty cool. Okay, is there a common line item in a DoD requirement that is challenging to meet? Oh, let me expand it. Is it challenging to meet, and why? What DoD requirement do you all see in your conversations that is the most challenging, and why? Anybody can take it. Go ahead.
Take that.
Max.
Again, speaking from the unique perspective of a small company, for us, it's future constraints on IP and manufacturing supply chains.
Ooh.
We have investor mandates to grow as big as possible, and the future constraints and encumbrances on IP ownership, margin rights, and you have to manufacture certain components in the United States. makes it impossible. I think we talked about this yesterday. Kyle talked about this. The majority of, for instance, of battery manufacturing infrastructure and mineral processing infrastructure exists outside the United States. We don't use anything exotic in our devices, but we still use things like nickel, and that comes from outside the United States. And most of those parts, if we're ever going to make them cost effectively, have to get machined or stamped offshore. And so for us, that has actually been a showstopper on 1 or 2 grants, because we said, hey, we can't endanger the future commercial price competitiveness of some of our components in order to take this grant.
Yeah, I'm glad you mentioned supply chain. It may impact you all too. I've worked with a startup called Sustainment, and they work with machine shops who, depending on where you are in the tiers of manufacturing, if you're a big, you're buying from tier 2s, and the tier 2s are searching for the tier 3s. But eventually you get to a point where those shops, and I lovingly call them the ma and pa shops, cannot meet the standards of the CMMC requirements because they don't have the capacity to track it. I mean, their CTO, their HR, their teams are the owner, the one person that's been overburdened with a lot of these regulations. So I'm glad you mentioned supply chain, how hard
and
that
I'll
is.
add to that kind of a call to action. Kyle hinted at this yesterday. If the DoD, you know, as a force for purchasing in the world, can engender industrial infrastructure for a lot of these fabrication technologies that have been offshored, that would be great. And, you know, candidly, when we buy something from China, the amount of IQC, incoming quality control, that we have to do on that part quadruples. And it takes us a lot longer, and it costs more to do that because we don't trust the suppliers there. So that is definitely kind of the con of getting these cheaper parts.
Yep.
And being more cost competitive. And so to the extent that the DoD can engender and incentivize a lot of industrial production and capacity to move back into the United States, or at least into our allied countries, I think that's a really powerful call to action.
It is. I would say that it's also probably at the highest levels of the DoD and Congress. So as I look to the two of you all, I want to go back to the idea of this, you know, power, human power performance for the soldier, and DoD requirements, and what gets in your way and why or how. What does that look like?
So I'll chime in, and I'll echo the supply chain, that we opened an office in China so we could work with Chinese battery companies, because that's where 80% of the batteries are built, right? And there's nothing more more simple about it than that. And hopefully that's not going to stay that way. But we had to. But on the other side, I would say, don't be bashful about being aggressive with your challenges to the industry. The conformable arable battery, the Army put in a requirement for a nail penetration test. All the suppliers griped and moaned, and then they provided a battery that would survive the nail penetration test, right? So I would say, don't be bashful about being aggressive. If you find one guy that can do something, the other guys will find a way to do it also. So, you know, stick it to industry a little bit, stick it to us. We'll come up with a solution. Right?
Yep.
And I'm thinking about safety in particular, but energy density and safety go hand in hand, right? They're inversely proportional. More energy is less safe. So I'd say stick it to us, right? Ask for more energy and put it in a package, and then demand it past some abuse.
Okay.
Right?
Doug.
Well, I think I'll echo the supply chain stuff again. We've had similar challenges. It's really hard to come up with an alternative than offshore suppliers. I think I've yesterday when we were in a panel discussion, I beat this drum. I won't beat it again here. But for us, I think one of the things that does trip us up is the sense that when we're applying for a small grant, some of the requirements that are written in seem like they're tailored toward a pre-existing solution that's in the imaginable. And sometimes when you're proposing something that is unimaginable or so completely different, it's really hard to fit into that box. And so that's one of the challenges that we find. And what I find really refreshing about this event here is the ability to meet face-to-face with the requirements writers and the end customers, so to speak, to really understand their pain point, and then propose our solution in a way that addresses the pain point and not the way the requirements are written, right? So I think that's really been our trip up here.
Yeah, but to those that are in the requirements world, that is one of the hardest things to do.
Correct.
is to describe in state without dictating how to get there. So here's a question that pulls off the supply chain thing, because I think it is interesting, which is, so what infrastructure technologies does the DoD need to invest to bring that offshore supply back here? Okay, we identified 80% over there, but what could we be doing here? Or what could the DoD, with their purchasing, incentivizing, is that a word? Incentivization, do to make that happen?
I'll volunteer first.
Go ahead.
Right. So I think the reality is we've spent decades offshoring a lot of this stuff, right? The center of electronics manufacturing is in Shenzhen, China. There's no way you can take it back in an instant. But what we can do really quickly is stuff like assembly, final assembly. We can bring that quickly over here, because that's, you still source the main boards or the PCBs offshore. In the meantime, you can bring the final assembly here. Why is that important? There's a lot of stuff that happens at final assembly. I mean, testing, some of this stuff can be proprietary testing, right? So bring it onshore at least allows you to have that final bit of control. So many times I've had to travel to the factories in southeastern China to realize that they're assembling stuff completely wrong, completely opposite to what we've specified. And that's always a surprise. Having it here doesn't mean that that kind of problem will go away, but at least it's a 2-3 hour flight as opposed to a 12, 14 hour flight.
So the takeaway is, while the production might still be overseas for quite some time, we can bring more assembly back. Is that the takeaway?
That's my take.
That's your takeaway. Max, you want to say?
Yeah.
Brian, go ahead.
So one thing the military does really, really well is NRE, right? Non-refundable engineering. It's the development costs. Occasionally, we've got a couple of consortium members who have battery production lines that were built by the military, and they're not allowed to use them for other sources. And so the line sits idle 70% of the year because it's not allowed to be used. And so I would challenge the military to, yes, fund the production facility for your critical materials and devices that you need, and then be able to demand access to it when you need it, but allow it to be used for other things when you don't. Because, we all know you need a certain amount of stuff when we're at peacetime and 800 times that much stuff when we're at wartime, right? The ratio is pretty big. So you need to have the production capability there, but let them use it for the rest of the world, because what they'll do is once they're using it, they'll buy another one, right?
Yeah. For me, that's a great takeaway, because it happens a lot in the private sector, even without the Army requirement to not use it. There's just a lot of overcapacity in manufacturing, and unless you match supply and demand together, we have idle equipment going around. Max, anything to add to that, or hop into another question?
I'd add two things.
Go ahead. We'll let you have two.
Pardon?
Not three, two.
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 Yeah, two.
Go ahead.
Only two.
Okay.
I promise. So one, I think, is rapid prototyping. This is something where, frankly, we have rapid prototyping shops that can do exotic materials, weird ceramic stuff, strange new alloys in 3 days in China, 3 days in Vietnam, and you ask for the same quote from a US or Canada-based supplier, and the quote is 16 weeks. And the reason for that is because the other person who's buying that is at Lockheed Martin, right? And no offense to Lockheed, but they're big and they're slow. And I think most people would agree on that, because they have, they know what they're doing, and they don't take risks on kind of rapid prototyping and new technology. And where they need to do that, they have the money to bring it internal. So for us, that's been a big struggle.
Number two,
talent. A lot of the talent that knows how to deal with weird materials and high temperatures and so on has been offshored now. A lot of the aerospace technology, let's put it this way: everybody's kind of hunting and in a war for talent. To the extent that the DoD can engender certain critical both technical hands-on skills as well as knowledge bodies into curriculums, I think that could be a really good long-term kind of feeder and pipeline for enabling rapid innovation and technology development and transfer to the DoD.
Yeah, I'll actually use moderator privilege to respond to both of your points. Number one, sustainment.tech, that was the company I was talking about, are going after that very problem of being able to find rapid prototyping. And right now, most of it's overseas, sustainment.tech. And number two, about talent. This is a very sad state of where we are right now globally. And as long as this record's been kept, it's about 40 plus years, for the first time in their record keeping, more international students chose Canada than the United States. More international students chose Canada than the United States in the last time they took the poll in 2020. We cannot, if we want to keep a competitive edge technology-wise, let that keep going. We've got to get back number one and keep that going. Okay. Oh, good. More questions came in while we were talking. Let's see. This is going back a little bit more towards the technology piece. Well, there's 2 or 3 of them. Let me just pick one that kind of sums up the others. So what's the plan in your innovation that enables next gen battery if the requirements for next gen doesn't exist? So how do you build for the technology that's not there yet? Or more importantly, the requirement that's not there yet? Go ahead.
From the DoD perspective, I think the key to deal with that is really to work with people behind the scenes in a less formal capacity. So
Which
yes,
people?
People who are thinking about the 2030, 2040 DoD strategy and start having the informal conversations about what the future could look like and what innovations are required to get there now. And start building those into some of the commercial technology roadmaps. So as a CTO, I own our technology roadmap, and I say, okay, in 5 years, we want to be here, right? And of course, there are huge error bars for anything 5 years from now. But I have a mental map and kind of written down map of, okay, these are the kind of R&D next gen areas that we want to invest in to be able to do that. If I had DoD folks who came to me and said, hey, I think your technology is really cool, I'm envisioning this future scenario. What can you do? And started that conversation now about 2025, 2030, then I think that we could start to build some of those things into our roadmap. The challenge, of course, is do those overlap with very large purchase orders in 2030? And what's the guarantee of that? Inherently, there will be none 10 years from now. But to the extent that we can find ways to overlap those with where we think commercial technology is going, that also increases the odds that those kind of new innovations get incorporated into our tech roadmaps.
Yeah. So this whole conference being hosted by AAL, that's their whole mission. Jay, just to put you on the spot, he's talking 20, 30 years out. What's your window horizon that you all are looking? 3 years. So keep that in mind in terms of expectations of where they're thinking. But there are people in this room that are thinking around the corner. And I think so what you're proposing is a drink at the Driscoll Hotel later on this afternoon for you to explain and have that conversation.
Yeah, and
Okay.
I'll add to that just to clarify. I meant 2030 as in the year, not 20 to 30 years away.
So 7, 8
5
years.
years away,
Okay, all right.
right? But if you have things that you want in 3 years and you want to see that innovation, we're open to that too, right? The challenge is how do you guarantee some commercial return on it for us to invest in the development? And I say that again as a small company.
Yeah.
I would add too that yesterday at the breakout session, one of the conversations was, well, hey, we're working on these roadmaps, but I can't really talk about it yet. And I think that that's fine. I get why you can't talk about it. You don't want to necessarily put a line in the sand and then have to walk it back. But conversations along the way where, different groups outside are involved in building that roadmap from the beginning, I think would be really helpful and more transparency.
Yeah.
I'll just add to that a little bit.
Please do.
So as a fellow CTO, I like to develop what I call tech trees, right? Technology trees for the company where one building block leads to another and how things merge together. I mean, that's how how I plan 2, 3, 4, 5 years out. I encourage the same kind of conversations. And I'd like to kind of flip the question around a little bit. I mean, what does next gen mean? Like, what is the pain point that you have with today's batteries? Let's understand that first. And then let us in industry try to be your eyes and ears and try to help you see connections and overlaps between our commercial paths and your longer term goals, right? So if we can find a path to map our commercial technology trees with yours, then I think it's a win-win, right?
Yeah,
Okay.
a lot of the conversations.
Let me
Oh,
go
sorry,
over here.
ahead.
No problem.
Yeah.
Over to Brian real quick, get his thoughts.
Yeah, so I would say to use the systems you've got now, which would be SBIR and the BAAs. When I talk about innovation, I always talk about kind of two concepts. One is to be humble about where you are, not overstate where you are, but be really bold about where you want to go. And so I think from your perspective, we need to know a real wish list, not a modest wish list, but a bold wish list. And then the other thing is to kind of unburden the SBIR and the BAA system. There's a lot of effort put in to make sure nobody spends the money badly, but that prevents us from spending it well. And honestly, it makes a whole bunch of people who otherwise, including our company, who otherwise would participate, just not mess with it because of the administrative burden. I mean, how many times do I want to count the hours for a $100,000 grant, right? I'm just not going to put the system in place to mess with it. So throw some money at some crazy ideas, demand some results, but don't worry about the hours and minutes and a few dollars here and
So
there.
we'll go to you in a second, Max. But that's one of the things that I've enjoyed over the last 10 years working with startups over and over and over again is to watch this cycle where somebody has an amazing idea. And again, this is not just DoD innovation. I'm in energy and transportation and mobility leader development. But in every case, it takes somebody to believe in the big, bold idea, the big, bold dream. If you are not thinking bigger and bolder than where we are right now, we're literally doomed to stay in the proverbial cave. So I appreciate your comment about that. But it does come with failure. And what is one thing that politicians and check writers not like to deal with? Failure, because somebody has to explain it or be accountable for it. We need to create a culture of more learnings from things that don't quite go right. So, but anyway, Max, you wanted to add something?
That's okay. You actually covered it. Both
Oh, good.
times.
Okay. All right. Well, in fact, Brian, this one's actually coming back to you next, talking about the battery consortium itself, which is how are you all working to standardize batteries in any way, whether it be form factor, size, weight, or to recognize the downside to potential innovation, but can be advantages?
Yeah. So one of the things that we're doing as a consortium is to do kind of what I just said, which is to set a bold goal for battery safety. Battery safety standards today are, I'm just going to use the word pathetic. They do not, every battery fire that you've ever read about in the news happened to a battery that was certified to today's battery safety standards. So we set one as a group, and this was part of the founding of the company, the founding of the consortium. We set one that has far more damage abuse done to the batteries, and we require them not only not to catch fire, but we require them to continue to function 4 hours later. We're calling it kind of level 1 to battery safety, and our intention is to come out with a level 2 standard 2 years from now, and hopefully we can upgrade every 2 years. And I kind of mentioned that analogy between, anti-lock brakes and seat belts and airbags, that each time we set another level, there's going to be something else required. The next one's probably going to be some sort of not required as in you got to put the material in, but required. We're probably going to require some high temperature abuse, and not just abusing at room temperature, but abusing at high temperature, which is going to change the materials that'll be able to satisfy that standard. So that's one thing we're doing, is we're just going to set the standards higher and expect the industry to respond, right? And here, my thought is, look, if you're going to buy a baby monitor for your kid and one of them's got the safety sticker on it, one of them doesn't, it doesn't matter what the one with the safety sticker costs. They're going to buy it, right? So I think the safety sticker, that's the other thing we're doing, is if you can be certified to the standards, you can stick that Soteria name on it. Soteria is Greek for safety. And that's the idea, is that once there is the safe one, who's going to buy their daughter the car that's $5,000 cheaper but doesn't have the safety sticker, right? I'm not, right? I'll either not buy it for her or buy her the safe one.
Yeah. I haven't been in a Humvee in 10 years. I have to admit. Are the batteries still underneath the TC seat? Okay. I can't tell you how many times I had a little hot seat having to hop out and apply fire extinguisher quickly. So, okay. By the way, we can still take more questions. And I know we started early. Are we ending early, or do we get to keep on going? Keep on going. All right. So keep sending your questions. And as you can see, we're taking this a little wide range beyond just the personal power performance. We're getting into some larger subjects. So I can use moderator privilege and ask a few of those questions too, since these three certainly know what they're up to. Let's see. we talked about, oh, this is an interesting, if I've already asked it, I apologize because I may have answered it in my brain, so forgive me for doing that. But how are you working to integrate your technologies into existing products so that the warfighter can continue to use those devices that work and still benefit from the advanced personal power generation that you provide?
Oh, it's for me, right?
Any one of you.
Okay. I would say that that's possible, but it's really quite tricky because we don't know what systems there are, and frankly, whatever we found out is that it's really fragmented. There's contractors who do X, Y, and Z, and another company might supply A, B, and C for nominally the same purpose. So it's really challenging for us to do that as a whole. What we found more fruitful is to just actually provide that entire application in one single bundle. It doesn't help solve the problem, unfortunately. So I don't really have a good answer for that.
Yeah. Well, no, I think that's the whole point of this conference. We don't have a good answer yet for it, which is why AAL convened it, which is to figure out how to take your technologies and figure out the best ways to integrate with the systems that are already established. Because at the end of the day, it's okay to have one or two systems that work, but we're a 1 million person army and we got to scale.
I'll add one more footnote, right?
Footnote.
What we have been doing is to create standardized solutions for our industry partners. So in as much as those standardized solutions can help provide power, I think this is something that could work. For example, we have the power energy harvesters that apply those sensors, the remote sensors. We are actually providing that as its own unit to a different group. And maybe that can help you solve your sensor problem. Maybe you don't want to use our sensors. You want to use your sensors. You could use the energy harvesters. But it's frankly, it's not as plug and play as we would like it to be.
Yeah. Okay. Anything else to add to that?
I echo that completely.
Okay. All right. So this next question literally makes me shudder. There's a reason why I live in Texas. There's a reason why I married a Texan. There's a reason why after I had her 2 years in Boston in grad school and 3 years teaching at West Point that she said, I shall never winter again, which is why we live in Austin, Texas. Albeit last year's extreme, unbelievable. Okay, so this question talks about the fact that operations in extreme heat was mentioned, but what is being done to address operations in extreme cold? And I think the person wrote -65, but I'm just going to pretend like that number doesn't exist. What do we do in extreme cold? How do you all perform? Each one of you have an application.
What's the unit, Fahrenheit or Celsius?
Again,
I don't even want to look.
It's
Go
almost
ahead.
the same at that temperature. So for us, it doesn't matter. Our technology is super high temperature. So think like 900 Celsius plus. So it operates with a combustion flame. So as long as you have a fuel that's not going to solidify at that temperature, which most of the compressed gases will not, then it's fine. So that I know is one challenge that people are working through with diesel, and in that case, you might need to switch to some other fuel. But I don't know quite as much about how the batteries or thermoelectric stacks work in these kind of extreme conditions.
I mean, very similar to you. I mean, the thermoelectric itself is fine. If we're truly batteryless in a certain application, then we don't have to deal with the battery side of things. That said, there are batteries that we specifically select for a larger temperature range. The lithium titanates, for example, you can go higher, you can go lower in temperature. But yeah, it's on the generation side for us, it's not a big deal. It's just the storage side that is a little bit more challenging.
Okay.
Yeah, for batteries, the electrolyte is the issue at those low temperatures. They freeze, and the best thing you can do with any energy that you've got at those low temperatures is warm up the battery. So if you have any energy in the battery at all, you use that to warm up the battery because the function of the battery will get better a lot faster. That's the best way to get energy is to warm up the battery. So from a personal power standpoint, I'd say cuddle the battery.
Anybody here live in a climate where they have to have the battery warmer or blanket for their car at their house? Okay. Yep, okay, not bad. My idea, 5 minutes? Okay. My idea of cold And this is how soft I've got, you know, try to be cool, Ranger school and all that stuff back in the day. The other day, I brought home dinner for my wife. We're going to settle in for movie night. Bush's Chicken, if anybody knows Bush's Chicken. I got the big 32 ounce, all that little small ice cubes they have. They're just fabulous. The only thing to make it better was just a little shot or so of Tito's. Put that in there, bit vodka. Put a little Tito's in there. And it got so cold so fast that I went to try to drink my Tito's and Diet Coke. It literally had frozen in the straw and I created a dam. And that for me was a problem. So to read a temperature like -65, whew, I've gotten soft. Okay, let me go back up to some of the other questions we missed because they were starting to sound a little similar by quick reading, but I'm going to go back in and ask a couple of them here real quick. I think we talked about this real quick, but just assuming a perfect efficiency, what is the max watts that could be harvested from an individual's body heat?
Well, the human body puts out about 100 watts, right? So maximum efficiency is 100 watts, right? A light bulb. You're never going to come close. So what we deal with is to really squash down the sensor systems to be consuming microwatts, milliwatts, right? And that's where you can actually start to make a difference in the lifetime of your sensor system.
Okay.
Right.
Very cool. Anything
Somebody's
you want?
boss is calling.
What's that?
Somebody's boss is calling.
Oh, yeah, no, it was Darth Vader. So if you know that person and you know their boss, text them right now. And if it's their spouse, don't do that to them. Don't do that to them. Don't do that to them. Okay, so 2 minutes out. Let's go ahead. No new questions that came in. And I'm sorry if you asked a question I didn't get to. The longer your question, the harder it was for me to read up here to preview. So I apologize. But these 3 will be here at the conference all day today, right? And so you can, what's that?
Today's my 20th anniversary, so I'm leaving early.
Catch them. That was Darth Vader who called and said, I'm tracking you on your phone and you haven't left for the airport. So just get to that. So closing thoughts, 30 seconds or less. Start with you, Max, go across.
There's a lot of heterogeneity in armed forces use cases. The easier it is to unpack those and find solutions and map the problems and the demands that you all are facing onto our technology, the better. So if folks, call to action, find ways to do that, find ways to unpack and distill, and we'll help you get there. We'll help you build the future. But it would be very helpful to have more understanding of what your, top needs really are.
Very cool.
I'll echo that. I'd like to understand what the true pain points are beyond just what's written in any requirement document. And I like to try to solve it in a completely different way than what most of us have been accustomed to by doing stuff completely different. Maybe we can get rid of these battery requirements, but maybe we can, going to Brian, change the way we think about batteries too.
Okay.
Yeah, and I'd say I've this week learned a lot. The breakout yesterday was great for me to get an understanding of what the needs are in the military. And the sad thing is I've been in the battery industry for 10 years and somehow I didn't know. And so my challenge would be, hey, get out there and tell your story. Go to some of the regular trade shows and tell the story a little bit, because there's people out there who want to hear it, want to understand what the pain points are and don't know, and so aren't applying their intellect to it, right? So, right, we will come to you guys, but I think also you should get out and tell the story. Right?
Yeah. And the last thing I'll leave you with is, as I told you when I walked up here with this cool little mic on the side, I was going to dance like Madonna. And it's not just because of the microphone, but it's because of how much I enjoy being in this space. What you all are doing is hard. And it is probably the most important work of our nation. You need only look at the Ukraine and Russia to understand in real time why what you're doing is important. So for that reason, I applaud everyone for being here and the continued work with AEL and all that they do. On a personal note, this is my jam. Like I said, this is what I love doing. So as Nick said, when I came up, I work for the president of the University of Texas on all things military, veterans, and families. As I like to say, it's everything from helping folks with the GI Bill all the way across to, world-class research and development for the next art of the possible and everything in between. I don't do any of the work. I just use those 2 languages, military and civilian, to try to find the people on campus to marry up with you and vice versa. And then on a professional note, this is what I do. I mean, I work with companies to help them think it through with my company Gray Line. So if there's anything I can do to help you all in this bridge to figure this out, I'm happy to help you all there too. So Jay and Nick, the whole crew here, thank you very much for having this panel today. Thanks, guys.
Thanks, Nick.
Thank you. And another great jacket. I didn't get the message. Great jackets.
Tomorrow is going to be sporty. Okay. Hey, everyone. I really appreciate that was a fantastic panel. We're going to break a little early for lunch, so we got a little bit more time, but please be back by 12:30. Veronica Stelmach is presenting. She's the CEO at Mesodyne, and she's going to share some technical insights on how revolutionized power generators can address demands for reliable distributed power today and in the future. So I'll let y'all go. Let's go get some lunch and then come on back at 12:30. Thanks so much.
push that button when it's green. You're
Okay.
good. Actually, give me a test.
Check.
Toggle.
Hello.
Oh, I need to move that a little,
Okay.
just a touch.
Hello. 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 Hello.
I need to turn up the gain on this guy.
Hello. Well, I'll probably speak a little louder
Okay, I can hear
during
you
the.
now. Yeah, yeah, yeah.
Okay.
Cool.
All right.
Sick.
Seems like it works.
Mhm.
Okay, I'm excited for your Thank you. Thank you.
Okay. Hey, folks, we're going to go ahead and get started. Some folks are still trickling in. Again, I apologize for probably the rush to lunch, get to the keynote, which is tough. But hopefully we're maximizing your time here as well. And it seems like the reason why people are coming back slow is they're having a lot of really good conversations outside of this too. So I think that's good. Next up, we've got Veronica. She's the CEO at Mesodyne, and she's going to speak to the technical insights and how revolutionized power generators can address demands for reliable distributed power today and in the future, right? And so her company has really done a bunch in the thermovoltaic arena, and she has with the potential to address issues in long duration mission sets. Like UAVs, dismounted operations, areas with low light. So I think it's valuable for us here. Again, very smart person working with very smart people to solve some energy constraints in the extreme environments. Without further ado, I'm going to introduce Veronica. Everybody, round of applause.
Thank you very much. Can everyone hear me? Okay, great. So it's so great to be here. Thank you for the introduction. It's really a privilege to have the opportunity to speak to everyone. So my name is Veronica Stelmach. I'm the CEO of Mesodyne. At Mesodyne, we're building a new kind of power generator that converts fuel to electricity via light. And it enables reliable, compact, long-endurance power anywhere, anytime, and from any fuel. But I'll come back to that actually a little bit later. First, I was going to talk about a little bit some of the solutions that have been implemented today for soldier power. And I've been studying actually soldier power for the past 10 years, starting with my PhD at MIT's Institute for Soldier Nanotechnologies, where some of this work started. And we already heard yesterday that electrification is really hard. It's really hard on the battlefield where there's no access to grid power. And electrification of small things is even harder because they have to be so compact. And the only solution we really have today is batteries. And batteries, we just heard, also have reached pretty much their thermodynamic limit. So what can we do today to extend the range of batteries that we have available? And the thing that we do have is fuel. We have JP8. How can we use JP8, which is 60 times more energy dense, to extend the range of batteries today and in the near future? And so that's the focus of my talk today. And the Army has looked at a number of different solutions to try to solve this problem. And naturally, the first thing that comes to mind is, well, we have internal combustion engines in cars and tanks. Like, why can't we just take a large internal combustion engine, divide all dimensions by 10, and use that for the soldier power system? And the problem is that the way that the internal combustion engine works you have a piston that compresses a fuel and air mixture. You have a spark that ignites this, and the combustion heats the air, which pushes on this piston and does mechanical work. And when you reduce the size of that piston, you actually end up with a lot of different loss mechanisms. You have basically less fuel that's in the piston, so you don't get it to be as hot. You have a phenomenon called quenching that prevents the fuel from burning on the walls, that also causes a lot of issues. And so basically, you can try to increase the RPM and get this spinning really fast, but then that ends up being really loud, unreliable, and noisy. And actually what you end up with is a weed whacker engine. And that's not really what you want to bring with you on the battlefield. And then in addition, even with the engines that are more sophisticated than the weed whacker, when they're so small, we still see that the maintenance on those is about 100 hours. After about 100 hours, they break down or they need some kind of overhaul. So that's really only about 4 days continuously. So that's still not good enough. So, if engines are out of the question, what else can we do to keep these batteries charged on the soldier and on the go in these austere environments? The Army has looked also at solar panels and wind turbines, but of course, the sun is not always available. The wind is not always available. You can't always, unroll the blanket and wait for 5 hours if there are trees and things like that. So that's not, again, a reliable solution to this problem. So probably the most work that has been done here in the past 25 years is in fuel cells. And we've heard a little bit about them yesterday. And fuel cells, especially hydrogen fuel cells, can be very good for large stationary applications. But when you try to use fuel cells at the small portable soldier power level, again, you run into a lot of issues. And so there are two kinds of fuel cells. The first one is the proton exchange membrane fuel cell. And this kind of fuel cell, you need a proton to cross the membrane. And hydrogen essentially is just, the ionized hydrogen is a proton. So you need hydrogen. And the problem with hydrogen is that it's so light that you need a really large fuel tank. That's okay, again, for stationary applications. But then, unfortunately, for soldier power, what can happen is that it actually outweighs literally the advantage of using the fuel cell, because you're having to bring this really heavy, ruggedized hydrogen tank. So you could, in principle, use methanol, but methanol has half the energy density, and there is no available logistics chain for methanol or even hydrogen. So really, that's the biggest problem. There's no hydrogen available on the battlefield today, and probably not in the near future. We heard yesterday, probably not for another 10 to 15 years. So again, what can we do right now? Well, another kind of fuel cell that's been developed is the solid oxide fuel cell. And that kind of fuel cell uses oxygen to pass through the membrane to generate electricity. So in principle, it can work with most hydrocarbon fuels. But in practice, it actually doesn't. And you end up having to use a reformer, which causes another issue because it's large and adds complexity. And then even with solid oxide fuel cells that can run on propane without a reformer, they need a catalyst, which is very sensitive to sulfur. And so you still have to use ultra-pure propane. Ultra-pure propane is not available on the battlefield. That's another logistics problem that you have to deal with. So if fuel cells are out too, what else can we use? And so we just heard about thermionics and thermoelectrics, and I'm not going to go into those because you have the experts here. You can ask them questions. At Mesdine, we're using a different way to convert heat to electricity. It's called thermophotovoltaics. And so it's a conversion of heat to electricity via light. And in our design, a small microcombustor heats a photonic crystal emitter to incandescence, and the light from the photonic crystal is then converted to electricity by low band gap photovoltaic cells to generate electricity. That sounds really complicated. So does that really, what's the advantage of doing it this way? Well, there are actually a lot of advantages. The first one is that you can, in principle, get very high energy density because you're leveraging the high energy density of the hydrocarbon fuel. So you can beat batteries by more than 10 times in terms of energy density. The other benefit of using our technology is that you can actually use JP8 fuel today. You can, in principle, use any fuel because we're just combusting the fuel. We're not, doing something electrochemical. So that, of course, has great advantages because there's JP8 available today. And then another benefit is actually that the way that we burn the fuel is different from an internal combustion engine. It's a very high temperature combustion, and so you end up completely combusting the fuel. So there's no smoke, no soot, no particulates. It's a complete combustion of whatever you're burning because you're burning it at 1,000 degrees C. And so another benefit of doing it this way is that it's a solid state conversion. So there's no noise, no vibration, no things that you get basically from the moving parts of the internal combustion engine. And finally, the great thing about this is that you can build it as modules and then have different scaling possible. So if, for example, one soldier carries a 50-watt light cell, and another one carries another 50-watt light cell, they can come together and now they have a 100-watt generator, but then they can separate again and carry their own power. And you can go up to a few kilowatts currently and with the current system. And then in principle, this technology can scale even beyond that. And I guess going back to how it works, the way that we do thermophotovoltaics is different from how it's been done historically. Historically, TPV has been limited by the fact that the radiation that's coming out of the heat source or the microcombustor is mismatched to what the PV cell can convert. And so you end up with low efficiencies. And we actually solved this problem by using a nano-engineered photonic crystal material that reshapes that radiation to only emit the wavelengths that can be converted and suppress the wavelengths that cannot be converted. So again, at the core, we have the microcombustor. The microcombustor's job is just to heat the photonic crystal emitter. The photonic crystal emitter is emitting light, and then that light is just converted to electricity by photovoltaic cells. So your output is similar to what you would have from a solar panel, but you can use this system any time without needing the access to the sun. When we initially demonstrated this technology at the Institute for Soldier Nanotechnology, we were working on a pretty small system. It was actually a 1x1 planar microcombustor, and we were working with propane, but we demonstrated 5 watts of electricity out in this small microcombustor. And that's actually what started our company. But as we grew the company, but also the actual light cell to some more useful output power above 20 watts, it turned out that there were a lot of challenges to go from the small microcombustor to the larger light cell. The first challenge that we encountered was actually at the microcombustor level. It turns out that you can't, the original microcombustor was planar, and you can't really scale that beyond a few tens of watts. So we had to switch to a cylindrical system that could burn fuel. And then actually burning the fuel turned out to be a lot more difficult than we had anticipated. We were originally running on propane, which burns very easily, but switching to JP8 actually required a fundamental redesign of the microcombustor. And it actually took years to get to now today when we're able to burn the JP8 fuel. In addition to the challenge of burning the fuel, you have the challenge of extracting the heat. The photonic crystal needs to be at about 1,000 degrees C to emit the right wavelengths that can be converted by this low band gap PV cell. So you use the exhaust from this small microcombustor to heat this photonic crystal. And then the heat that's rejected goes back into a recuperator to preheat the incoming air. And so now you have this self-contained system, and your exhaust is actually at a safe temperature. But we had to develop this system because, in a benchtop, initially we didn't have the recuperator. In addition to the microcombustor, of course, the biggest challenge is also the photonic crystal, which is the key critical component in our technology. That was actually the focus of my thesis at MIT initially. And when we did the 5-watt 1 by 1 centimeter demonstration, I fabricated all the photonic crystals myself, and I thought that this was, a good path forward. But there was actually a lot more steps needed to get to a process that can be easily manufactured in a standard semiconductor clean room. And the reason that we need a standard semiconductor clean room is because the photonic crystal is actually a piece of metal with really small holes, and the holes are matching the radiation that you're trying to enhance. And so you have to use a semiconductor process to etch these holes into this piece of metal. And you also have to use standard lithography to be able to make this pattern of holes. And so we are now at the point where we're using a standard lithography system, a standard etching system, and so we can make these photonic crystals at much larger scale. So that was another big challenge for us before. And then once you've fabricated this photonic crystal, the next challenge is to integrate it on the microcombustor, which, as I mentioned, is a cylinder, but your photonic crystal is a flat piece of metal. So we had to actually develop some processes to be able to roll and bond these photonic crystals to our microcombustor. And when I say bond, it has to be completely bonded to the microcombustor because any gap will cause a loss in efficiency. And so we are able to do that now. So again, that was a big challenge we had to overcome. And then the final technical challenge is actually a little bit also of a supply chain challenge, but it turned out that the photovoltaic cells that we're using, they're low band gap photovoltaic cells. They're not standard silicon solar cells. They're the kinds of cells that you use in satellites in space, and there's only a few companies today in the US that can manufacture these kinds of PV cells. So it took years to develop relationships with the right companies, develop the designs that we would be able to manufacture with them, and then once you have finally the cells, there's also the challenge of actually integrating them into a module that could work with the light cell to efficiently extract the heat. And so that was a big technical challenge that we also overcame. So in addition to all these technical challenges, there's all the challenges of growing a small business, especially when you're a deep tech startup. There's little capital that's available, and the timelines are long. And so, we wouldn't be here today if it wasn't for the support of the government. Initially at MIT, we were funded by the Army. And then today, as Mesodyne, we've been funded through, now we've received more than $5 million in government grants from the Air Force, DARPA, Department of Energy, and NSF. So we're very thankful for that. We've also raised our first venture capital round last year. So that's been great. But even when you have money to build the thing, now you'll still need people to want it and customers. And so that also took a while for us to be able to build partnerships with companies that believe in our vision and want to be at this bleeding edge of technology. And we're now excited that we've partnered with a large defense prime to bring this to the warfighter. And we will have a demonstration this summer that I'm happy to talk to you about after this, if you're interested. But okay, so that was a lot of challenges, and there are still more challenges to come, I'm sure. Actually, one of the main challenges for us right now is looking at how we can bring the cost down of the solution, because I'm sure you're all thinking, well, that sounds pretty expensive. And actually, one of the biggest cost factors for this is just the PV cell. And so if we can bring the cost of the PV cell down, we can make this solution pretty much attritable. And so we're really excited because there's been a lot of news recently in thermophotovoltaic storage. Maybe you've seen an article in MIT News that was talking about a new PV cell for Tpv storage that was 40% efficient. We're really excited to be able to leverage this kind of PV cell because that's the exact same PV cell that we're using in our system, or this is the kind of PV cell that we need in our system. And so we can leverage that. And so the thing about the Tpv storage application is that it's different. It's not using a microcombustor. It's actually using the electrical grid. When it's producing too much electricity, you can heat a large thermal vessel essentially to stay really hot. And when you need that electricity back, you can capture that with these low band gap PV cells. And the difference here is that you need pretty much a football field of these photovoltaic cells to get the kind of megawatt power that you're looking for. And why that's great for us is that as these companies and universities are building these much larger quantities of PV cells, we can leverage that cost reduction. And so we're really excited for these companies to be developing that. So bringing it back to the actual solution. So the light cell is a small portable generator. And the idea is that it's about the size of a water bottle for the 200 watt, a large Nalgene bottle, not a little water bottle. But the way that you would use this is, for example, for a soldier squad, currently they bring about 124 pounds of batteries is what we heard. So if you were to now reduce that battery load to maybe 1 per soldier, and then just bring this generator plus fuel, you can actually reduce the weight carried by 86 pounds or 70% because of how much more energy dense this generator and fuel are. Another application where this is really, we think, helpful is for small UAS. So for example, a fixed wing UAS today that's flying for 2 hours on battery power could fly more than 24 hours if you were to reduce the size of the battery to something that can account for takeoff and landing, and then put a small generator and then pack the rest with fuel. And actually, you could fly more than 24 hours if you're able to put more fuel on. And maybe some of you saw recently the Stalker flew for 39 hours on propane. They attached a tank of propane to the wing, and they were able to fly for 39 hours. Well, at Mesodyne, we would be able to do that with JP8. And so that is really our value proposition for the soldier, is that we're looking to enhance batteries today with what's available today on the battlefield, which is JP8. And the light cell isn't, a one-size-fits-all solution. In fact, I don't think any technology is a one-size-fits-all. And so if we're going to solve the problem of power, we're going to have to use new batteries, new fuels, new generators, and really apply them to the appropriate application and at the right time. And so at Mesodyne, we're really excited to be a part of the solution. And I'm really excited to be here today and learn more about all your applications and see how we can work together on bringing this to the warfighter and enable reliable, portable power generation anywhere, anytime, and from any fuel. And then I'll take your questions.
Thank you so much for that talk. That was wonderful. I'm fascinated by the workings of that. For folks in the audience, reminder, you've got QR codes on the backs of chairs, so you can go ahead and submit your questions now. I see some coming in. Veronica, can you tell us more about the expected power density of the system? For example, a 10 kilowatt unit, do you have an idea of how large and how heavy a system like that would be?
So we are focused on the smaller end of the power spectrum. Again, sort of in the range of maybe 20 watts all the way to a few kilowatts. 10 kilowatts is probably pushing it, especially today. But the energy density, first of all, that depends on how much fuel you're bringing. So let's just say that if you're looking at, you know, a few day mission, well, and it depends if you're looking at the UAV or the soldier power use case. So it's inside the vehicle. Okay, so the vehicle, you know, essentially the problem with the vehicle is that it does require so much power. So this really is more if you were using it silent. Yes, silent watch. Okay. So for a silent watch system, you're looking at an energy density of somewhere in the 1,200 watt-hours per kilogram. So, you know, the weight of the system. Yes. So the device itself, without the fuel, so the 200-watt light cell just weighs, in principle, 3 pounds. So it's very small, just the actual generator, because all you have is a small microcombustor. And then to give you an idea of how it scales, the output wattage is directly proportional to how many PV cells you have in the system. So the 200-watt has about this many PV cells, and they're kind of formed around the microcombustor. So then you can just scale that and then extend. But there's some practical limitation to how big your unit light cell should be. So that's why we're thinking that, you know, we probably wouldn't push it past 500 watts for the unit light cell. And then you can combine the unit light cells together to, for example, yes.
Thank you. Our next question, is looking at the dual use potential of this technology. Do you see market opportunity in the commercial sector for this technology, or is it primarily a soldier-specific type technology or product?
So it seems like there's a lot of interest in at least industrial applications, where more and more we have, you know, sensors and the need for reliable distributed power in locations where we don't necessarily have power. And so things like telecommunication, you know, construction, those are the kinds of industries that have expressed interest in on the commercial side. And then that's also because, you know, this device is pretty expensive still. So as you're able to really miniaturize this and productize this further and bring the cost down, there are a lot of more applications that open up in the commercial and consumer markets. And of course, there's commercial drones, which, you know, they're obviously taking off, but at the same time, there's not a clear value proposition still for some of them. But you know, sort of mid-mile delivery, drones that are a little bit on the larger side, on the commercial side, that's definitely also a market that we're looking at. And then just within, you know, the military markets, it's not just soldier power, it's soldier power, UAS, counter UAS, you know, different kind of border security. You know, there's a lot of applications, obviously, that need power.
Thank you so much. Our next question is wanting to know about the overall energy efficiency converting JP8 to electric. And there's another question here, I think, dovetailing in. Can you help us understand the trade-off point of where this type of conversion from fuel to electricity is better than traditional generators or small generators that we have now?
Yes. So I guess the first part of the question, so at MIT, when we were doing the small microcombustor, which was 5 watts, we burned 100 watts of propane and we generated 5 watts. So that was about 5% efficiency. And that seems kind of small, but actually, even with that, you're about 2 times better off than with batteries when you're going on the 72-hour mission. And that's because the trade-off point is the weight of the generator. So as long as you have you need to bring at least as many batteries as like your generator weight, you start to see at least it's either equal or a benefit. And then the longer the mission, the more benefit you see in using you know, this with the battery. So it's sort of after 72 hours, that's really where we see that taking off, and then enabling capabilities that are just not possible with batteries today. So like the 1-week mission, on the go charging, things like that. And so going back to the efficiency of the engine, so the larger engines have a pretty high efficiency today and they are pretty reliable. But the problem is that when you scale the engine down, as I was mentioning, you have all these losses. And so even the best engines today in the small portable form factor are, maybe 10% efficient. In fact, many of them are in the 7% efficiency range. And so that's also where we're at today. But there is the definite path to a higher efficiency, starting with the improvements that we're making now with the system. And so sort of the predicted efficiency near term is 15 to 20%. And then longer term, we can reach about 30 to maybe 40% efficiency. It doesn't sound like a lot because people are used to hearing, I want 99% efficient, but it's actually about when you're capturing that much of the caloric content of the fuel, you're getting a huge advantage over what you can do with batteries alone. And in terms of comparing it specifically to the internal combustion engine, again, it's not so much an energy density because in principle, the engine has high energy density. But the main problem with the engine is that you can't miniaturize it. You can't use it reliably. It makes too much noise. It's not solid state. It has vibration. So I guess we're not competing on necessarily efficiency with the internal combustion engine. We're competing on efficiency with batteries, and we're competing on other things like noise and things like that with the internal combustion engine.
Awesome, thank you. And we got time for maybe one or two more questions here. Can you talk more about the temperature of this device, like to the touch, and the exhaust temperature, and how that might interact with soldiers who are wearing it or carrying it or using this device?
Yes, so I guess that's one of the challenges that we didn't think too much about when we were transitioning from the benchtop to the actual real product initially. And so once we started working with this large defense prime, it became a much bigger issue. And so this is something that we're definitely investigating more now. But the short answer regarding the exhaust is that, as I mentioned before, we do this loop where we're recuperating first the exhaust to go back through the system. So by the time the exhaust exits the device, you're looking at maybe 150 degrees C, and that's how it is just straight out. You can actually cool it down further by just having a pipe or even adding a little bit of airflow. In the drone, it's not even a problem because the drone is flying, so it's generating enough airflow to cool it down immediately. So even in our benchtop experiment today, you can put your hand in front of it, but I do understand that is obviously a huge concern. And so that's something that a partner that I've been talking about, we're working with them on the productization of this and basically making it into a usable device for soldiers, and also doing a lot of the testing that we never actually did before, the fog and sand and all these new exciting, environmental conditions that I hadn't heard about before.
Thank you. And maybe a last question here. Currently, this system is designed for JP8. Are there any challenges preventing this system to be used with gasoline or diesel that a consumer or civilian can use?
Great question. So because we're just burning the fuel, we can burn any fuel in principle. I mean, JP8 is probably one of the hardest fuels to burn. So if you can burn JP8, you can burn diesel, you can burn gasoline, you can burn just about any liquid fuel. And so we've demonstrated it now with diesel and JP8, and on the liquid side, Coleman liquid camping fuel. And then on the on the gas side, we've used propane, butane, and basically, the main difference is going to be the efficiency of the burn. So it's going to be slightly different for the different fuels. But and then the main difference between, say, propane and JP8 is that you actually have to vaporize the fuel. And so vaporization of JP8 was the biggest challenge, especially at this scale and at this temperature. And so again, if you can vaporize JP8, you're pretty much good with all the other liquid fuels. So, yes, we can use different fuels. We can use biodiesel if it becomes available. We can even burn hydrogen in principle if that becomes available. But again, our main goal is to enable something today with the existing logistics fuel. And so that's why we've been developing this for JP8.
Veronica, thank you so much. Again, can we get a round of applause? Thank you so much.
Thank you very much. Thank you. Thank you.
Okay, awesome. We have one more panel today before we go to breakout sessions. I got a couple of instructions on that as well. But thermionics meets wearable tech is next. And I think they're all mic'd up, so we shouldn't have any delay as I bring these folks on. Also, this panel is like really tricky. When we were working through the right folks to get on the team for this up here, the moderator, all those things, it's a tough one to try to find those right folks for this. So I would definitely be asking questions. There's definitely on the panel a broader experience from different perspectives. So I'd be excited about some of that. I'll introduce the moderator for this. He goes by VB because if I tried to say his name, I think it'd be really terrible. I'm not going to do that. He goes by VB. He's the associate professor and Carl J. Eckhart Fellow in Mechanical Engineering at UT Austin. Right here. Good to see you, sir. And he has a background in thermal sciences, management, energy, water systems, oil, gas assurance. He also has got some experience in R&D from GE and currently teaches courses on heat transfer and fluid mechanics at UT Austin. Please welcome VB.
All right. Good afternoon, everyone. Thank you for being here, and thank you, Nick, for this introduction. It's my pleasure to be here chairing this panel. And again, I'm an associate professor in mechanical engineering at UT Austin. I mean, I look more like a student than a professor, but that's besides the point here. And again, I'm delighted to welcome the panelists on stage. And we have Giri Joshi, who is a senior scientist from Nanomics. We have Shannon Sentel, who is the CEO of Stealth Power, and Josh Seagroves, who is the co-founder and CTO of Parasanti. And again, the idea is that we'll be talking about thermionics, we'll be talking about wearable tech, and some of this was covered in the previous panels as well. But there are many other topics that we'd like to discuss, and especially things like data analytics and the Internet of Battlefield things and all the other related stuff. So again, I'm excited to start this panel. And I'd first like to begin by having the panelists introduce themselves briefly and talk about their backgrounds and what they bring to the panel here. So Giri, do you want to start first?
Sure. Thank you. First of all, it's great to be here. Thanks for this opportunity. My name is Giri Joshi. I'm from Nanomics, which is just another side of Colorado River. I'm working at thermoelectric technology since 12 to 13 years. But in that time frame, I have also extended my work, research work, especially in energy harvesting technologies, cooling and heating technologies, power generation, especially waste heat generation technologies. Yep.
All right, Shannon, please go ahead.
Good afternoon, everybody. I'm Shannon Sentel. I'm the Chief Operating Officer and Lead Engineer for Stealth Power. We're a Austin headquartered company that does hybridization of any type of internal combustion engine you can think of, from Class 8 trucks all the way down to standalone generators. We provide a hybrid solution along with a full suite of data analytics to do some predictive AI on systems that we're installed in. And we exist on systems everywhere from the city of New York. Every ambulance in the city of New York has our system on it, to every border surveillance tower that's not watching the wall and along the southern border from here all the way out to California. A little background on me: 24-year retired Army officer, armor officer by trade, moved out of that into congressional affairs and finished up running the physics side of physics and nuclear engineering at West Point. That's my last assignment in the Army. Just happy to be here with y'all.
All right. Josh, please go ahead.
Hey, good afternoon. I'm Joshua Seagroves, the CTO and founder of Parasanti. We're a local Austin company as well, if you can't tell from my accent. I may have to, if you ask a question you can't understand it, I'll try to use some different words, but please ask again. Here at Parasanti, our main goal is to really bring that next generation data fabric to the battlefield, to the oil field, to these remote and extreme places. Throughout this conference, I've heard all kinds of great battery technologies, power technologies, but if we can't connect those, we can't bring those together, and if we can't get the insights out of those that we need, we're just going to fail in deploying this in the future. My background, I was also Army. I was a counterintelligence agent. Spent a lot of years for our 3-letter agencies, doing all kinds of work there as well, and started Parasanti about 3 years ago. Great to be here.
All right. Thank you, everyone, for the introductions. And again, I'd like to start by discussing thermoelectrics, because that's what one of the keywords for this session is. And so this idea of thermoelectrics have been around for a pretty long time. And I'd like to get a sense from you on what are the current challenges in this field, and what needs to happen to move from where we are right now to what the Army will need for the next generation or for the next decades to come.
Okay,
So Giri, do you want to
Yeah.
chime in?
As you said, thermoelectrics is as an industry, it's for almost 50 to 70 years. As always, material fundamental efficiency is the main problem. However, last 10 to 15 years, especially the academia has done pretty good job. And now the efficiency of those materials, all the way from very low temperature application to all the way to high temperature, has increased significantly. Still, it's way lower than other competitive technologies in the range of 10 to 15%. But that opens right now a lot of application, which could be niche application, but there are no other alternative can be available in that case. For example, NASA RTZ application, they have been using for a long, long time. Like that, in case of especially the Army application, past 8 or 10 years ago, I think thermoelectric power generation was in research pretty heavily. And at that time, it was just at the first stage, they were just making the system level engineering, because most of the thermoelectrics focused was academia. Very few company was focused on system level device engineering. Those kind of thing was not happening at that time. Once that 10 to 15% efficiency happened, after that, there has been work going on, and waste heat of battlefield trucks, especially, which is heavy and can accommodate a little bit bigger size, plus tanks. Those kind of thing could be a good application for thermoelectrics for generating power from waste heat, which we otherwise just wasted. Plus, which is this panel is about wearables. We are at Nanomics now, right now, working as a cooling side of the thermoelectrics to cool the body by using just your wearables. You can wear and heat or cool according to your extreme weather. But in the meantime, those thermoelectric devices also can be used to power localized sensors, which could be autonomous. We might still need battery because of the fluctuation of temperature difference it requires, but it will extend the battery life way longer compared to that. But having said that, especially in wearables, I have seen a lot of work going on last 5 to 10 years. The main challenges is when we see the body temperature and outside temperature, there is a big gap. But our skin is not good conductor. So ultimately, there is a very few delta T is available in the range of 1 degree Celsius. But even that is efficient or efficient enough to run very small sensors like environmental sensor. We at Nanomics, in fact, did one of the Air Force research. Just around 1 degree Celsius can run environmental sensor, which is required, which might be important for Army at the battlefield, or some kind of communication devices. So it's going very slowly, but based on whatever we have right now, just changing the engineering of the devices and application status, where we want to use. There are some application thermoelectrics can be used at this time. But academia, always they are focusing on material research, which we should always be focusing on, because as the efficiency goes on, opportunity goes always more.
Okay. All right. So we've talked about thermoelectricity and the use of potential use of that for powering sensors. Now, what are the other sensors that can be powered and that would be of use to the military and to the army in warfighting situations? And I'd like to get inputs from the industry folks on the panel who have experience in this area.
So just to go off of your point on material, I'll be very brief.
Okay, sure.
As you said, a lot of the work that's being done now is in academia. There are certain commercial ventures, a government venture specifically. NASA just put a rover on the moon, one going to Mars that has a nanostructured material that is leading to a much better energy density or power production capability because of its influence on the lattice structure inside the material. I don't know how deep we want to go in here. It looks like some folks are smiling that might smell what I'm stepping in, but you want, you want low thermal conductivity, high electrical conductivity, and a good Seebeck coefficient. So those things can be altered at the nanostructure by working on engineered materials. And that's where I think we can, as industry, pool our resources, pull together and make that leap. Because if we can make that delta T better between those two materials, then you're going to see the amount of Q go up that you're able to pull out of these devices. So to the point about what we can wear on the battlefield, I think we were trying to frame this in a way where we talk some materials, those things, and then bring into the people in this room where they're going to have to pull all this together. I saw in my time on the battlefield all of the things that had to be wired together, and then we finally went to things that had a small amount of communication, very limited distance where they could talk to each other. We're talking about putting something 1/100th of the size of an Apple Watch and embed it in the collar of a soldier's uniform, or have them wear it somewhere on their body. And you can go and read numerous dissertations out there about where the best place to wear this or put it is on the body. We're trying to get to the point where that, and to Jerry's point, not either have to have a battery or have a battery that's very, very small, given the current chemistry restraints that we're seeing, how small we can make a battery, an air battery, if you will, that will hold this very small amount of power, of energy that's being produced, and then release that to those sensors. And I'm not going to steal any of this man's thunder, because that's what he does for a living, making those things talk to each other.
No, and that's a great point. In the Internet of Battlefield Things, you've got soldiers being deployed. They are now wearing compute. They're wearing power. They're wearing these sensors. You've got to be able to bring these together in a holistic approach. Being able to have commanders communicating with their soldiers, understanding their power needs, understanding your other needs, being able to run those insights right there. So being able to have that data fabric is very important in all of this and bringing it together. I think both panelists actually brought up, how all of this comes together, how all of this works, together. It's a problem that we're actively working to solve. And so, that's one of the biggest key things that I see is, we have industry here, different protocols, different languages. Being able to bring all of that together, to get that insight, to get those understandings, I think is one of the issues that we're working out solving.
Okay, so in terms of edge computing, I think that's where your specialization is. So what does it do to this data analytics and predictive capabilities and offering real-time insights that
Yep.
cannot be enabled otherwise.
Yeah, no, absolutely. So, luckily we are getting some more advanced power capabilities that allows us to have this compute with us. We're getting smaller and smaller compute, less power requirements, less draw to be able to do those analytics that you need. So being able to connect to all these different things, to be able to understand, because the soldier needs to understand the environment around him. If he shows up somewhere new, we already have sensors on the ground. Let's get those connected. Let's get the soldier more insight, but also all the way up to the commanders. It's a huge problem, and definitely something we can work together to accomplish.
Okay, and
As far as the edge is concerned, we do that on a couple of systems that we have now to make decisions that we can let a user know. Get a couple of examples where we don't have to send data all the way back for it to be crunched somewhere. It can be analyzed, at the point of collection, make a decision there, and then let someone know, or let the person wearing that device know, so that they can make a decision. A couple of examples are just accelerometers, different types of things that might pick up vibration differences on alternators for an internal combustion engine. We see something outside the range of normal, we start to analyze that, and we might send a text to a fleet manager that says, hey, vehicle 1, 2, 3, 4, you're probably going to have a problem with this alternator in 6 or 7 days from now. You need to bring it in now before it's stuck on the side of the road. So that's the kind of edge that having that type of either small storage or power generation at the point where the edge is taking place is going to make the difference.
Well, I mean, you brought up a great point. The cloud is not on the battlefield.
Yeah.
The clouds in Northern Virginia, Washington, here in Austin. You got to worry about the connectivity. Cloud's not going to be able to handle this. You're going to have that edge compute that is small, that is portable, that's energy efficient to be able to draw out these insights that you're going to need. Absolutely.
I want to add one interesting point. What we're trying to do, in fact, alternator or any equipment, there are different places localized. You have a vibration as well as most of the places heat too.
Mm-hmm.
So there are certain energy harvesting technologies which can go together, especially a part of thermoelectric device can be a piezoelectric device.
Okay.
So using those kind of device in that place would easily power whatever power is required, and the edge computing will provide that data wherever we need that. So I think the power generation would be one of the key in that case, and wiring there would be really difficult as it is right now. So I think the localized power is becoming more and more important based on what we need as a requirement.
okay, so talking about localized power, and we're talking about data processing, data analytics, compute, and what are the power requirements here in the sense, how much would a soldier need deployed on the battlefield? I mean, are we talking about milliwatts or watts or more than that? So
That's a great question, and luckily we've made a lot of progress in reducing the power consumption of some of these compute edge devices, some of that compute hardware. So right now we're seeing a little less than 5 watts on a soldier. And that will still provide you, the capability to draw out insights from hundreds of sensors, right? But as we work to get that smaller and smaller, to be able to compute what is exactly needed, and being able to give you that insight on how much power the soldier needs, that it goes back to the original why you need edge compute for that. But yeah, right now it's less than 5 watts. I'd love to see it in the milliwatts, and really be able to deliver some of these. You've got sensors, for instance, that's using, they'll wake up, they'll use a few microwatts and then go back to sleep. But for that compute, it's always running. It's always going. It's always bringing in that data around and crunching those numbers. So, right now, unfortunately, it does require a lot, but I think we're seeing a really good progress on bringing that down.
okay, so you're talking about 5-watt compute requirements, and I think one of the panelists in the morning said that the human body generates 100 watts, and that's the maximum you can harvest. So I think in principle, it's possible that you have a self-sustained soldier which does not need any external energy inputs, that is essentially getting all the data that is required to help him or her perform efficiently on the battlefield. And what's the status of like thermoelectrics, for example, in getting 5 watts? I mean, is that realistic? What do we need to do there?
I would say not now. So I can add that 100-watt point. So that's from the whole body. That's the heat radiation. So basically, if we want to think about thermoelectrics only, which we don't need to, we have to put that thermoelectrics everywhere, all the way, right? And the 5% efficiency needs lots of delta T. So basically, if you go in literature and see most of these wearable power generation devices, most of the results are, for some reason, I have no idea why that is, but either some were 70K, some were 50K, or some are even more than 100K data, which have nothing to do in case of wearables, because wearables case, we hardly get 1K. So efficiency will be way, way lower than that. And in terms of, I think the first thing is, do we really need that 5 watt together? Because we are trying to do localized and more dissociated, right? In that case, if we do localized and we have other options, like something is always moving, like piezoelectric, or there are other technologies like coming right now, which are still new, but they are also getting attention. So we have to capture all those and get that all needed energy. If we do that, I think it's possible in future, of course.
Okay. All right.
The environment has a lot to do with it too, where the actual sensor is, what the delta T based on ambient, and then where it's placed on the body. If you can get a better airflow across it, obviously with the heat sink there, that you're able to have that larger delta T. As you said, it's about what, 1K for one micro.
1 Kelvin is already a good number for
Right.
delta T, because the body core temperature around 37, skin hardly get around 33, 34. So, and the main thing we rarely discuss in terms of system, there is always a lousy heat transfer between the body and whatever material we put there, aluminum or whatever device. And you have some safety related issues. So you need to have some low thermal conductivity materials. So all that, when we count all those things, then delta T will be pretty low. But yeah, I mean, there is a possibility. Yeah.
Okay, so continuing on the topic of environment. So again, we're talking about conflicts happening possibly in the Arctic in the future. And again, at the other end of the spectrum, you have the Middle East, where it's hot and dusty pretty much all year round. And how ruggedized do these sensors, and I'm talking not just thermoelectrics, but pretty much everything else that you've discussed, how ruggedized do they need to be? And can the same sensor work in the Arctic and also work in the Middle East, or does that need different kind of solutions? And I'm just talking about the extent of customization that is needed. And I'd like to get your perspectives on all of this.
Particularly thermoelectrics is pretty good in terms of
Yeah.
certain temperature range, from very low up to 200 Kelvin to all the way to, based on the materials, right? If you are talking about Arctic to Middle East type temperature, the well-known material bismuth telluride works in between 200 Kelvin to all the way to 400, 450 Kelvin pretty well. So thermoelectrics is pretty good. Piezoelectric materials works pretty well too. Most of the material commercially using are pretty high temperature. Apart from that, yeah, I do not have other new technologies, how those are temperature related, but specifically thermoelectrics should be fine.
Okay.
We do not need to custom, but we might need to custom in terms of your delta T and how you design your device itself. That might be needed based on the scenario.
That's where I was going to go with it, because in a cold environment, if you do have a sensor, think at a more tactical level, sitting against the skin of a service member, and you have layers and layers and layers of material on the outside of it that's specifically designed to keep the TH in, and you're looking for TC, which is a cold place, there's not a very easy way to get from point A to point B in that through that layer. Same thing in a very hot environment. The soldier's body temperature is going to go very high. It's not going to go, to what you're going to see with your TH, or your TH, but it's not something that's very easily done. We are just starting. There are people decades in front of us on doing this, but I mean, just the problem set that we're looking at is how do you design something that actually fits against the skin that's not in a piece of material. We say wearable material, but it's actually one of the most inefficient ways is to embed it inside something that a soldier service member is wearing. It's just the efficiencies drop off a cliff when you place them in a piece of garment or something like that. And you also run into all kinds of things of T-shirts being switched between people and not having, Specialist Jones and Sergeant Smith having different T-shirts on, and you're trying to get Specialist Jones's vital signs, and he's actually wearing Sergeant Smith's T-shirt, and that creates a whole different set of problems for you.
No, and I think it's a great point. You need to be able to operate in all these different environments and all these different conditions. You really want your data to work as hard as you do. And so to accomplish that, you're going to have to start making, materials, hardware, things like that can sustain these different temperature swings, the different environmental conditions, the dust, the heat, the cold, the rain, all these things. When I was in the military, right, I had a uniform, and that uniform I would put on extra clothing when I got cold. I would take some off when I got hot, but it was still that same uniform. So, we got to have, it working as hard as we do.
Okay. So, again, if there are any questions from the audience, feel free to turn them in, and I'll wait for my iPad and we'll run through that. But in the meantime, I wanted to talk about, again, on the analytics part of things. So talk about artificial intelligence and machine learning and how that can improve the quality of predictions and essentially give you more for your buck. And are these things being deployed actively, or do you think that there's room for much more advancements in this topic?
There's always room for improvement. Always room for improvement. We're seeing it now. We're seeing, being able to do these predictive style analytics before a soldier goes out, be able to get those lessons learned in real time, because a soldier is a walking network, a compute, so being able to do that. We definitely need some advances. You want to get the compute down. You want to be able to use less power. You want to be able to talk to those different sensors, different other capabilities out there. So all the standardizations, the specifications, everything that we have to go by, is only going to work to improve.
To go to that, I think outside of all the things that you could collect based upon sensors and a weapon or whatnot, I think the actual personnel things that you can collect is probably one of the most important things to focus on, not only just the health of the person from a physical aspect, but their behavioral status, how we can make an assessment of soldiers that are actively involved in very high dynamic situations, kinetic situations where a lot of things are going on both physically, but in their mind, and help leaders make decisions instead of having to find that out later that someone was not doing what they were supposed to do with no eyes on that. All of those things can talk to each other and make decisions. That's on the personnel side. And I've kind of alluded already to the hardware side. Anything that you can do to better inform someone that a piece of material is going to have a failure or break before it happens, especially in those very dynamic situations, is always good. And if you can do that on the front edge, as opposed to processing that somewhere else and then getting a report as you're sitting in a vehicle that's not working anymore, that's always goodness.
Absolutely. Absolutely.
Instead, we are working mainly for how to make that work more efficient and how we can accelerate that kind of probability in soldier body. So yeah, for the device side, how we can improve that, that's the main goal for our case. And not only thermoelectric, but what else is available as a energy generation. That's what we're trying to support for that data processing process.
Okay, so continuing on with data and analytics. So then we expect to have a lot more data floating around a soldier. And I suppose cybersecurity becomes really important. And we hear things like in Ukraine, the Russians are using unsecured communication channels and they're pretty easy to intercept. And how important is that in the context of what we're talking about, getting all this data secure and our clouds really secure, and do we have enough security, and is this a topic that deserves attention going forward?
I think it absolutely, you have to pay very attention. Soon we're going to have it where, you can take a soldier out just by hacking their system.
Yeah.
Not, and when I was in the Army, you usually got taken out because you took a round or an IED. But now in the future, you're going to be able to shut that soldier down if you're able to hack in, get access to that data, get access to those sensors, not only stealing that data, but providing wrong information could have, very detrimental effects on the battlefield. So security should always be first and foremost in everyone's mind. We're seeing it with the grid. The grid was hacked just a few months ago. We're seeing it across the board where, security was not taken seriously. And, because of that, the lapse or it was easy or whatever, I understand completely. It's hard sometimes to secure your network. It's hard to secure your data. But if you don't, the repercussions of that can be, life-threatening. And I don't think the cloud is going to solve that. That's not necessarily a cloud problem. One of the things that we like to talk about is most of the data you have in the cloud, only a few percentage, 40 to 50% of that data is actually being used. The rest of it just sits there, right? Just open for attack. And that we see it with the TransUnion and Equifax and all these other organizations. This data just sitting there where it's not been processed, it's not been enriched, it's not really been used. When the future of the battlefield, we're going to have all of these sensors, all of these networks on that soldier. You need to process it right there. You need to secure that data right there. Get the insights to the commander, not every piece of data into the cloud.
But just two quick points there. One, we've got to have a network set up where the equipment that we're talking about now, much like the chips that you find, or basically anything that's in any high performance aircraft nowadays, can be traced back to original manufacturing. I mean, we know the day, the person, the place, everywhere that every piece of equipment in an F-35 was made. We've got to make that kind of an effort. That's point one. Point two, the data has to be born secure. We have to make the effort to get it to where when it is created, the only people that can understand that are people that understand our encryption. And I mean, it kind of sounds pretty silly, but I mean, we deal with it on a daily basis with our border systems, constantly fighting every time a surveillance camera has an issue. It's like, well, it must be a power issue, or they've hacked our grid. And it's like, well, no, we're on AWS and Microsoft Azure on the high side. So that's not possible. So it's probably something else. And those are the 2 points I would make there.
Okay. Right.
I do not have any expertise on that, but yeah, one thing, at least as a general thought, once we are going as a data, then of course security is always important.
But that's a great point, though. I mean, as someone producing power or producing a product, you've got localized security right there. But then you also have the grander scheme of security across the board, being able to communicate, to be able to talk to those things, encrypt that data when you need to, things like that. So it's even. As industry starts bringing some of these products to market, it's got to still communicate.
Yeah.
All right, let's look at some questions from the audience. So again, there's a question: how many years out is this technology for inclusion on soldiers? And what should DoD be investing in that you're not currently seeing being invested? So I'll let everyone respond to this. So how far are we before thermoelectrics can be deployed on soldiers?
Thermoelectric technology, it's pretty mature technology in terms of thermoelectric itself. The only thing is not well studied is how to well design the system, for example, wearables or something else, which is also relevant to like a portable power, those kind of thing. There should be certain 4 to 5 years range of R&D, or at least study. I would say study rather than R&D, which never happened, or most of the time didn't happen. Most of the thermoelectric work, if we see all the way, it happened mainly for ZT improvement, or particularly efficiency improvement. In fact, I was I was thinking how old that is when Shannon was talking about that nanostructure. That was the first time we invented with JPL. And now we don't even realize that. That happens long time back in 2008, 2009, that nanostructuring concept. So yeah, there should be certain study should involve, especially wearables. And the risk level is low. I would say risk level is low compared to either it fails or doesn't fail, if it's a new technology, right? Because thermoelectric is already mature in terms of reliability. They're already tested multiple places. So it's ready to go. But the system level engineering should be studied. I think you had another question for what other technologies can be used?
Yeah, so what else needs to happen and what should DoD be investing in? So that was the second part of the question.
I think I mentioned a little bit on that part in the beginning. The waste heat is there in different form. And at some extent that happened, but that also same way, if we see that work previously, the work was mainly led by university. It never happened through most of the engineering firm or more engineering way. I remember we developed at some point 1 kilowatt long time back in 2014, but there was a problem because they were heavy. They were efficient, they were reliable, they were strong, but they were heavy. But there was never work done how to make those light. So I think one area, definitely the waste heat recovery, because there are logistic big trucks. They are burning fuel like every time. Anytime they are running, they are burning lots of fuel. And even right now, we can get 8 to 10% of efficiency, which is much better than previously. We have to invest on system engineering, and that is big in terms of energy production. Yeah, I think that's one I remember, at least, which could be very fast and which could be very developed in pretty soon.
Okay.
I would say the answer to how long is 13 trucks. Some people here probably know that answer. And then what needs to be done, it's the old adage. Wise guy said, resources follow priorities 100% of the time. So if whatever DoD needs to do to put money behind this priority will get it from point A to point B. The technology is there. It's a very mature thing. I mean, an old German guy came up with it, 250 years ago. So yeah, it's been around for a long time. It's I would say the two big stepping stones we have to get to are the miniaturization and the material properties. Those would be the two things I would say to focus on.
And there's not a lot I can add to the thermoelectrics, when that will be there. But when it does get there, as soon as I have an outlet, I have the compute on the soldier. As soon as I have that power, we're ready now to start deploying some of these compute capabilities, these sensor capabilities. It's only going to get better. But as soon as the power is there, that sustainable, reliable, microgrid that you're walking around with, we can bring that compute to the soldier. We can do those things in those harsh environments. So we're there with the tech. We just need some of that power to catch up a little bit.
And thermoelectrics notwithstanding, the ability to store that in a very small volume is also something that needs
Yeah.
to be explored, because if we generate it and it's not being used, it's wasted. And if it's not being generated and we need it, there needs to be something there to provide it in that interim.
Okay.
And just quick addition on that. I think most of the energy in battlefield, JP8, we burn a lot. So whatever form, either boiling the water or doing water harvesting, anything, wherever we are burning JP8 fuel, there is a probability of getting back some energy. And that could be used for localized some form of powering the system.
Okay, so here is an interesting question. This is not about someone wearing tech, but essentially using tech and sensors to track rounds and track how many cartridges are left, and essentially help out with the logistics. And again, is this something that is being done actively, or is that something that should be done and is not being done?
So I was actually at an event in Florida a few weeks ago, and I was really kind of curious on how far we have gotten in the sensors and the tracking of those. And then I ran across a company who puts a sensor in a bullet. It can tell you it has different sensors built in. It can tell you if the target's alive or dead, where it's located, things like that. But it also can tell you how many rounds do I have in this magazine? How many rounds do I have total is my soldiers running out of ammunition? And that's only one small aspect. Weaponry is now getting more and more sensors involved. The clothing we wear, the boots, you can see in the NFL, for instance, they've had it for 5-10 years now, where they have all these sensors in the helmet to tell you, did they take a hard impact? Is it concussion? Could there be a concussion there? Things like that. It's really encouraging to see some of these newer technologies come out, to track all of those different things.
I think it's got to be done. I mean, the population that we're dealing with now that is joining the military and will be carrying these things around requires it. I mean, not to be. I'll just say every first-person shooter game that kids play nowadays, there's a round counter and how many magazines you have left, and that's their mindset. It's always there. There's a piece of information for them that will dictate what their next move is. Am I going to get up and move, or am I going to have to go find some more ammunition? Yep. It's a video game analogy, but it's very relevant in what the future of the battlefield is going to be. I believe.
Absolutely.
Yeah. So there's.
No, I would just add, these days, information is a power. So we have to have that.
Yeah, talk to Zelensky.
Yeah, so this is, again, a question about thermoelectrics. And the question is, how is the system better than a radioisotope thermoelectric generator? So this is essentially what NASA uses in its probes. And
could you please repeat once again? What is better?
So again, how is your system? So again, we're talking about current thermoelectric systems, and how are they compared to legacy systems that NASA has already sent on its probes?
So NASA, most of the thermoelectric devices and materials are application specific. NASA has limited, since it needs to go to space, weight is the most important factor. It's related to cost too. Efficiency is very important. That's why, based on all materials, from all the way from bismuth telluride to all the way to high temperature lanthanum tellurides, there are many in between. They chose one of the material which is the highest efficiency, and also adding in layer, which is also called segmented scarudides and lanthanum telluride group, because the efficiency is high. They have a limited heat resource. They have to convert that into electricity. So they want to try to convert the best way. But when we talk about other applications, it's not always the same. For example, let's say the waste heat. Waste heat, it depends on what kind of waste heat it is. If it is low grade, means low heat flux, then yes, efficiency is still important, and we might be using some material like NASA. But some of the burning fuel, we should be using something else. And there comes our main focus was when what we are working is something like half Whistler based materials, they can be way more higher density compared to the material they are using at NASA, which is scleroids. The good thing is, if you want to use scleroid, you have to make bigger size material. And when you make halfway, so you can make very small, which immediately improves your power density, multiple way. So let's say we are burning some fuel, then you have temperature around 1200 plus. If the first, whatever NASA is using, that material will have a hard time to survive. So that is already out. And we need to have very stable materials, which could be one of the halfway slur. And that can, in fact, even though you are burning 1200 degrees Celsius, after all those fins and everything, we tested at certain environment, we get around 500 to 600, and which is the perfect scenario for halfway slur. And we can get up to 2 watt to 3 watt per centimeter square, which is very high dense and close to some of the battery form. So if we compare that, our materials, by the way, we work on all materials. I have worked from all the way from bismuth telluride to lanthanum telluride, but most of the application, the high heat source, we should go with different material than what NASA is trying.
Okay.
Because we need higher power density. That is related to cost, of course.
Okay, so I wanted to discuss 2 more topics before we wrap up. And the first one is about road mapping and in the field of tech and sensors. I mean, especially the industry folks. Do you know what you should be working on for the next 5 years, or is that something that you decide based on your customers, or is there a bigger plan that you generally try to dovetail into? So is there road mapping, or if there is no road mapping, should there be a roadmap for wearable tech and like 2030 out and 2040 out, and what should be done in that time frame?
Yeah, just a couple of points there. Probably everyone in this room is wearing some type of a wearable device. It might be in the form of a phone, but it's with you in your hand all of the time. Our company decided about 6 months ago that this was a direction that we were going to pull off as one of our technology horizons, what we call it, to go and see what's in the realm of the possible there due to our work with the Army to this point. So we're working on the vehicular side now. The next logical step for us would be to go to the soldier and see what's in the realm of the possible there, either through battery technology or as a next logical step, something that could be a small battery with a generation source on person. And that's what took us from there. We've a couple of material engineers, a really good mechanical engineer, and we're starting down that path. I mean, we're going to take all of the reams and reams of data that's been produced in the academia over the past 30, 40 years, try to condense that down to a very quick collection effort and see where the holes in the yard are. And talking with our DoD partners, I think that's probably the best way to get from point A to point B, because the smart guys, the academics, have figured it out. We just need to figure out how to put it together as a system, as he said, and then where's the money?
No, and that actually was a great point. And I just want to add a little bit to that is, we have a roadmap, for instance, of where this is going. And that roadmap is made up of what is the art of the possible, what is, what are the customer requirements and those communications that we're having. But it's also whatever we can dream up. There's one of the founding philosophies I have for the company is I really want to take care of my soldiers. I really want to take care of my farmers. Those are 2 dear groups that's near and dear to my heart. So being able to think of how can I help solve your problem? How can I make your life better? And work to get that into the roadmap. But I definitely think there's a mix of what's on the roadmap that your customers are supplying information on, things like that, but also what is that art of the possible? What are the dreams? What are some of these capabilities that we can think of? And having that open communication with the military, with, public and private sector, and then also the rest of industry, I think kind of helps drive that roadmap.
Any roadmap for thermoelectrics?
Yes. So basically, even though we're talking about that waste heat, the wearables But at Nanomics, we are working to little bit modernize thermoelectric devices. So we are making more modular and Lego type structure so that everybody can buy type Lego and connect together and use for most potentially for cooling and heating, because that's more immediate and easy application for thermoelectrics. But if necessary, that could be localized power too. So in the horizon, we are saying mainly one of the program we are now involving, which is pretty close to end product, is like a cooling jacket or cooling clothing. So thermoelectrics, we can make that a Lego to kind of conformal, and those devices can go to any clothing you want, and they can cool. Plus, if you are going in Arctic region, it can heat too. So whatever is required, that can be given. Plus, in the meantime, same wearables, if you are looking for localized power, and that is also provided. So over the 5 years, we will be focused on that part. But we are also trying to get, which is difficult, I guess many of us here know, which we always try to post, which is a little bit bigger in context. The power generation in waste heat is a challenge. And I think it's time we need to at least tackle it some extent.
Okay. All right. So I think what I want to do now is have the closing comments. But I think I'd just like to get feedback from the panelists on where we are with respect to some of our geopolitical adversaries in the world of wearable tech and thermoelectrics and sensors. So again, if you can comment on that, I think we'd love to hear it. So Giri, starting with you.
I can comment on thermoelectric since that's the field I'm working on. The material research-wise, the research outside US are growing pretty fast these days. That we can see in terms of what we were doing together in US. Are these people still in here? Some people already going that route. Specifically, material research becomes, it's long. It's already long, and it's like a stabilization phase. It's more like a saturated in US. But outside US, it's something like 8 to 10 time frame. So I think the funding level in material is way more outside. But in system level or in defense, I think US is still leader. I mean, I may not have all information. I may not go there. I may not know all, but system level, I think we still lead in terms of not only thermoelectrics, but as a system building, what we are using. I have seen some small fans burning. It's burning something, but it's a heater, but also running the fan, which is by thermoelectric power. Those kind of small application, we are using, I think, way more than others.
Shannon.
I would just, I would talk a little bit about batteries. Because that's kind of the field that I'm mostly involved in on a day-to-day basis. We could take the thermoelectrics, dump it into batteries, but we all know what the problem is with the ability for lithium or other rare earth materials to support the storage of said energy that's being produced by whatever source at this point. So for me, that's probably the thing. We can make all the systems adjustments, take that energy. We've got to put it into something that's reliable. And we all know where those materials come from now, whether it be lithium, cobalt, all of the other things that are very, very important. And I think we have to focus our research and our execution in a very short amount of time. I would say 5 years, or we are going to be in a very in a world of hurt, as my dad likes to say, on the battery sphere. It is a circle that is closing very, very fast around the United States and our reliance on lithium iron phosphate specifically. And thanks for listening. We really appreciate it.
Yeah, I don't have a whole lot to add to that, except for, the United States has to continue maintaining that information dominance. We need to be able to understand what's going on around us. If you look 5 years ago at the technology that was out there versus now, it's only improving. And the United States needs to continue not only investing into these new research topics, these new capabilities, but really creating that dialogue that's needed so we can understand the roadmap that we were talking about and things like that. I think we're on a bright future. I think there's a lot of room for improvement. But overall, I think we're doing a great job. And also, I just want to thank AAL, Army VERTEX. I love that this is an Army event, being a former soldier. And I think it's needed. We really need to start talking about these things. We need to start communicating. That's the only way we're going to be able to understand how that future, comes together.
All right. I think there's still a couple of questions, but I think we're out of time here. So I'll encourage the question writers to talk to the panelists directly. But I think this is excellent, and I'd like to thank the panelists for their time and their insights. And again, thank you all for coming in, and thank you all for your attention and questions. I think we'll stop here.
Yeah, same. Okay. Yeah. Thanks, Nick. Yeah.
Okay, so just a couple of new instructions for our breakout areas and sections today. So there was definitely some attendance changes from yesterday. We're going to have breakouts here at 2:30, and folks that are assigned those breakouts, you'll know because it's on the back of your badge. Please check them and then go to those locations at 2:30. So from between now and 2:30, that's what you should be doing. At 2:30, our Capital Factory staff will open the door to folks that want to go to a session. So if you aren't in a session today and you want to go to one, you can do that based on availability of that room. If there's extra seats in there, they'll let you in at 2:30. Okay? Please, if you got like more than one person in your group, I would split up and go to a different session each. Again, this is meant to kind of like give some folks another opportunity, a chance to discuss, have some good discussion in a smaller group setting. And this is definitely a place where you get a chance to have that dialogue to explore some of the problem sets that we're talking about from an Army standpoint. So exciting afternoon. There still will be some things here optionally going on. If folks are interested, that's on armyvertex.com as well. So you can check that schedule there. You can see when that happens. Official programming stops at 4:30 today, but there is a social on the 16th floor this evening at 5:30 hosted by Capital Factory in Parasanti, not technically associated with Vertex, but you are absolutely welcome and invited to attend. Thanks so much. Have a good afternoon, folks.